Welcome to Intro to Photonics. So far we have been talking about semiconductor light sources and detectors. So if you go back and see how we have progressed in this course, we started with characteristics of light, light propagation. We started with ray optics, went on to wave optics, and then we talked about the statistics of light, the random properties of light, and we found that photon optics is a nice way of capturing all those characteristics. And then we looked at interaction of photons with atoms, which was the basis for understanding processes like absorption and emission. We looked at absorption and emission in atomic systems, where we are considering these bosons, because it actually follows Bose-Einstein statistics. And then we went on to look at absorption and emission in semiconductors, where we are dealing with fermions, because it follows Fermi-Dirac statistics, right. And so now we know how to generate light, how to amplify light, and in general what are the characteristics of light. Okay. Now the last module that we are going to be discussing the next few lectures is, I will just put down the learning outcome. The learning outcome is identify the fundamental principles for photon, or in general light manipulation. Okay. So how can we manipulate light? How can we change the properties of light that we have? So for example, how can we change the intensity of light? So you have light emitted from a source, but suppose you want to modulate that light externally, right? You want to block the light for some time and let the light go for some time. Of course, you can do this, you can block it manually and then take it out, and you can do that, but are there any other faster ways of doing that light modulation? Okay. So those are the kind of things that we are going to be discussing in the next few lectures. And before we go into some of the specifics, let us actually go back to some fundamentals, something that you might already know, but nevertheless I will just for the sake of completion in this course, I will go through that. Question is, how does light propagate in a medium? We talk about light going through, let us say, an optical fiber, right. How does light actually propagate through that medium? What exactly is happening? To answer that, we will have to actually look at a microscopic picture. Let us just look at the picture of an atom, right. So you have basically a positively charged nucleus, and then you have these electrons that are orbiting around it. This is when there is no external field, no electric field. But if you have an electric field, okay, that is oriented like this, what happens to this atom, what specifically happens to this orbital is that orbital is now going to get influenced by that external, by that electric field, that the field that this atom is experiencing, especially the valence electrons, right. The valence electrons, the orbital is going to get sort of polarized. Okay. Now, that essentially means that there is actually a displacement of an electron in its orbital. It is still orbiting this positively charged nucleus, but there has been a displacement. Now, this displacement can be modeled in a classical mechanical system where you have a mass attached to a fixed point through a spring. Okay. And upon application of an external force, there is actually going to be a displacement that is happening. So, you would essentially displace the mass from its rest position. That displacement we will we denote as L. Okay. So, what is the corresponding analogy in the electrical sense is that there is a displacement of electron in its orbital. And if you are talking about an electromagnetic wave that is propagating through a material, right, you are talking about an electric field that is oscillating. Okay. And so, that electric field is actually changing sign. It is pointing this way at one instant, and the another instant it is going to 0, and another instant it is pointing the other way, and corresponding to that, that orbital is basically sloshing around. Okay. And when this happens at one atomic location, it influences the neighboring atomic location also, the valence electron in the neighboring atomic location. So, when we are talking about an electron sloshing this way, that will actually pull the neighboring electrons like this. So, the entire orientation or the entire material has this orbital that is moving this way, and with the electric field going the other direction, it is going to go like this. So, it is going to slosh back and forth. Okay. And this is as if you are taking one charge and moving to another point, and that is why you call it as displacement current. Okay. So, when you talk about an electromagnetic wave propagating through a pure dielectric, right, you talk about a displacement current that is happening. That displacement current is nothing but the movement or the displacement of an electron in its orbital. Okay. It never gets unbound. In a conductor, you would say that there are a bunch of sea of free electrons. So, when you apply an electric field, it actually moves these electrons across. But here it's not a free electron, it's still a bound electron, but it responds to a applied electric field. And that response is quantified through this displacement, and this displacement is what gives you the response of the material, which is characterized in terms of is represented or just say this displacement is proportional to the permittivity of the medium, the permittivity which you call as epsilon. So, all along you have been taking some value of epsilon for a material, and that permittivity is nothing but the response of the medium to an applied electromagnetic field, okay, electromagnetic wave. Okay. Now, what we want to know is what are the characteristics of this displacement. How does the displacement behave as a function of frequency, and how does the displacement behave as a function of the magnitude of the electric field that is applied. So, why is that part important? All along so far in this course, we have been treating the response of a medium to an electromagnetic wave, response of a medium to light, as a linear response, and that linear response is good only for a certain level of a certain range of electric field values. When you go to electric field values beyond that range, as in the case of this mass spring model, you are pulling, you pull a little bit, there is some displacement, you pull a little more, there is some more displacement. This displacement, if your pulling force is twice as the initial pulling force, then this twice the displacement. You go thrice, it goes thrice. You go to 1000 times the pulling force, the response is not going to be the same. It is going to start, not giving you a linear response. Okay. So, that is what we are talking about, that it could get into a nonlinear response beyond a certain point. We want to understand all of that. So, to understand all of that, let us look at this model. There is a question before we. Yes, yes. So, there is a question is there an exchange of energy which cause the material to heat up? We will go into the specifics a little bit in a few minutes, but suppose it's not able to respond as quickly as your excitation, there is a delayed response in the medium, right. So, if you pull at this speed, correspondingly the spring is displaced, the mass is getting displayed at that speed. Now, if my excitation is like this, that mass may not be able to follow that excitation. So, there will be a delay in the response, and whenever there is a delay in the response, you are essentially saying that there is some energy loss that is happening. Okay. That energy loss can corresponding to, one way of the energy can be lost is through heat in the medium, right. So, one way of explaining that is through absorption of that energy in the medium, and that absorption can generate heat. Okay. We will come back to that in a minute, but whatever is happening in an atomic scale, we are actually considering a classic mechanical model, because that model is probably fairly well developed. Okay. So, that might give us a little more insights about what is happening here. One of the things that we know as far as a model like this, where we have a mass connected to a fixed point through a spring, is the displacement is governed by the equation of motion, and the equation of motion says that the mass multiplied by the acceleration plus d, which is the damping coefficient multiplied by dl over dt plus S, which is the spring constant, multiplied by L, is given by or is equal to the excitation. In this case, the excitation force can be denoted as E times E lock, where E lock corresponds to the local electric field that this atom is subjected to, right. So, on the right side is your excitation, on the left side is the response of the medium to that excitation, the mechanical response of that medium to that excitation. That is the field that is existing, that the atom is subjected to that field. Okay. That field is essentially the external field, that is your electromagnetic wave, that is your light wave. That whatever external field that you are giving, there is a component of that present at a particular location, that is what we are denoting here. Okay. But we know we are interested in the propagation of an electromagnetic wave, and electromagnetic wave is nothing but it can be represented in terms of a time periodic function, right. So, if we for time periodic excitation, right, for time periodic excitation, which means that I am expressing the oscillation of my electric field in terms of e power j omega t. So, d is your damping coefficient, and S is actually your spring constant. So, what does it correspond to as far as this picture is concerned? You have a certain restoring force. What is the restoring force as far as an atom is concerned? There is actually a force of attraction towards the nucleus, right. That is your restoring force. Okay. So, that is actually like it is acting like a spring, and that restoring force, it may not respond in a linear fashion. So, there could be some damping involved in that, and that is what. So, this spring has got a spring constant S, and there is actually a damping constant also, d, that is denoted by d. So, for time periodic excitation, I am assuming that is, of course, it's a wave that we are talking about, but also it helps me get rid of all those differentials. So, d square over dt square I replace by minus omega square, and d over dt I replace by j omega, right. If I do that, then I can get, what I am interested in is an expression for L. Okay. If I divide this entire thing, entire equation by m, I can actually find the and do that substitution for time periodic excitation. I get an expression like this: E over m multiplied by E log divided by, there will be a omega naught square. I will come back and explain what this is. There is an omega square, this omega square coming from that first term, right, because we are d square over dt square, we are replacing by minus omega square. So, that is what is coming here, plus j omega, let us say gamma. So, in this I have introduced two new terms. So, what are those? This actually corresponds to a resonance frequency. Every spring that you take has got a particular resonance frequency. If you pull the spring and you let it go, it is going to bounce around and come back to rest, and it is going to bounce around at a particular frequency, right. That is going to be your resonance frequency, and that resonance frequency is given by root of S, that is a spring constant, divided by m, the mass, the mass of the particle that we are talking about. In this case, the mass of an electron, right. So, omega 0 is given by this, omega 0 equal to this root of S over m. So, that is why S over m we are representing as omega naught square, and this gamma is called the damping coefficient, and that is given by this damping constant divided by m. Okay. So, that is the expression for the displacement, and you can say that is with a proportionality constant, that also denotes the permittivity of the medium. But what you see from that is that the permittivity or the displacement is actually a complex quantity, right. It has got a real part and an imaginary part. Where does the imaginary part come into the picture? It is because of this damping term. And what does the damping term indicate? It indicates the fact that as you go to higher and higher frequencies, that damping term becomes more and more significant, which means that it is actually not able to, the displacement is not able to follow the rate at which your excitation is changing, right. Higher the rate at which the excitation is changing, more will be the damping, okay. Or in this case, you know, when you look at it, it's actually an imaginary, it's bringing in an imaginary term. So, that is actually the permittivity becomes imaginary quantity. So, what is that in a complex number, what does that imaginary component indicate? If you are looking at the response of a medium and you have a complex response. So, that imaginary component corresponds to a phase delay. If you do not have a imaginary component, there is no phase delay, there is only real response, right. There is no phase delay in your response. The moment you bring in an imaginary component, you are essentially saying there is going to be a phase delay in the response, and that phase delay is now dependent on frequency. So, this is the important part. Both your real part of permittivity as well as the imaginary part of your permittivity, they are both functions of frequency. We loosely say, you know, this material has a permittivity of 4. We loosely say this material has a refractive index of 1.5, right. Does that characterize the material completely? No, it does not. We are saying those values at a particular frequency. This picture tells you that all these numbers are a function of frequency. If you go to a different frequency, that value will be different, okay. Both epsilon prime as well as double epsilon prime, I can basically say, because this quantity is imaginary, I can say that epsilon can be written as a real part and an imaginary part. Do not pay too much attention to that minus sign, that is just a convention, but the key part is that there is actually an imaginary, the key thought is that there is actually an imaginary part to this. Okay. So, the permittivity is typically a complex quantity. Now, if I plot the real part and the imaginary part as a function of frequency, let us see how that looks. right. So, this is I am plotting the real and imaginary parts of my permittivity. The real part is, if I am just mathematically plotting this as a function of frequency, okay, and the x axis is frequency. Okay. So, if you plot this, then it is going to exhibit some behavior like this. Something like this. Okay. And similarly, if I plot my imaginary part, it is going to be like this, and then it is going to go through a peak here and a peak here and a peak here. Okay. And if I were to give some specific numbers to this, so this is in the order of 10 power 9 hertz, this is in the order of 10 power 12 hertz, this is about 10 power 15 hertz. Okay. So, what I plotted here, this is epsilon double prime and this is epsilon prime. So, interesting thing is, epsilon prime and epsilon double prime are related to each other. Okay. The specific relationship is called the Kramer's-Kronig relation, which essentially says that whenever there is a change in epsilon prime, that is the real part, there is going to be a corresponding change in the imaginary part and vice versa. Okay. All that is just coming from the expression for the displacement. Yes, there is a question. So, I am not putting down the question is how are we going to epsilon from displacement? Epsilon is actually proportional to displacement. Epsilon, or specifically epsilon r, the relative permittivity, is proportional to the susceptibility, 1 plus susceptibility is epsilon r. That susceptibility is directly proportional to this displacement. Okay. So, that is how we are tracing our way back to that permittivity. Susceptibility is a function of frequency, yes. That is what we are saying. The susceptibility is actually a function of frequency. But susceptibility we always, or we typically deal with only the real part. What I want to point out is there is also an imaginary part at certain frequencies. So, what does the real and imaginary parts mean? The real part actually, the root of epsilon r, the real part of your permittivity, relative permittivity, that corresponds to your refractive index. Okay. And the imaginary part, this corresponds to a loss term or attenuation term. Okay. So, one thing we see is that the refractive index is a function of frequency, and also there are specific frequencies at which a material will exhibit losses. Okay. And we see that there are there are 3 loss peaks over here. Okay. Out of which 2 of them are showing certain resonance. So, why is this a resonance? Because your omega naught and omega around these points, that actually changes sign. Okay. So, that is why it is actually going up and coming down. These things will change sign. But we are talking about not just one omega naught, we are talking about two different omega naught. So, what does that represent? Now, this actually represents the electronic resonance, which is what we have been talking about so far. We have been saying that this electron displacement in its orbital, right, that actually corresponds to a certain omega naught, right, that gives you what is called the electronic resonance. So, then the question is, what is this resonance? What does this indicate? Any guesses? What could this be? Mind you, this is happening at a lower resonance frequency compared to the electronic resonance. That is the clue. Yeah, this is the characteristic for a particular material. Any material that you take is likely to have these two resonances. First one is atomic, that is what we are well, first one as in the one on the left side you are saying, that is a atomic resonance, okay. Well, it involves atoms, so what we call it as a molecular resonance. So, molecule is made of atoms, you said two atoms, this could be modeled as two springs, and let us say if it has a covalent bond, it shares an electron between those two atoms, okay. So, that electron orbiting is essentially like a spring, so two masses attached to a spring, and that has its own resonance, okay. And in this case, in the electronic resonance case, we are talking about mass of an electron, but here we are talking about mass of an atom, right, because we are talking about two atoms and they are connected by a spring, okay. So, in this case we are talking about mass of an atom. Which one is heavier? Atomic mass is obviously heavier than electronic mass. So, that is why the resonance frequency, which corresponds to root of S over m, is inversely proportional to root of the mass, right. That resonance is going to be on the lower frequency side, okay. So, you have a molecular resonance and an electronic resonance happening for any material. Where they happen may change. A material can have more than one type of molecule. So, correspondingly you will have multiple resonances, multiple absorption peaks, right. So, a material, so we talk about silica, SiO2. So, SiO, that is a molecule, right. So, there is the molecular resonance corresponding to this, right. Now, you may have germanium also present in that. So, germanium with the oxygen bond, that is another molecule that might have a different resonance. So, when we talk about, remember when we talked about atomic levels, and we said these atomic levels could be signatures, or the absorption spectrum can actually be a signature of a particular molecule. We talked about absorption spectroscopy. Remember that? We said absorption spectroscopy is a powerful way of determining what is the constituent of a material, right. So, what we were talking about there, each of those absorption peak corresponds to one of these resonance peaks, okay. So, if you have multiple resonance peaks, you say there are multiple molecules, different molecules inside that material. Okay. So, you can identify them based on these peaks. Right. So, when we talk about vibrational frequency, that is the resonance frequency of a molecule, that corresponds to absorption at that particular wavelength, because when you give a bit of energy to that, it's actually it amplifies that energy to a point where it cannot follow that, it cannot keep on amplifying, it has to damp, and that damping happens in terms of heat. So, you lose energy through that. Okay. So, all these absorption peaks, all these loss peaks are talking about losing energy at those particular points. So, what is the significance between electronic resonance and molecular resonance? It is basically saying there are two species where this mass spring model is valid. Two species which respond to an applied electric field. Two species which respond to an applied electromagnetic wave. The absorption is essentially loss term, is what we are calling as a loss term. So, I should not actually call it a loss term, because it is not like every time it gives loss. So, I should just in general mention it as absorption. It basically excites that molecule and gets that to a vibrational state. From that vibrational state, it can actually give rise to light emission also, right, which is what we were talking about previously. So, you could actually have other energy sources coming out of that absorption, but epsilon double prime corresponds to absorption. Yeah. So, the first absorption peak is corresponding to the fact that your response it's not able to keep up with the frequency of excitation. There is a phase lag that is coming about, and because of the, so typically when we talk about a coaxial cable, for example, we say the coaxial cable exhibits high losses beyond hundreds of megahertz of frequency, and it goes to gigahertz of frequency. So, what are we talking about? In a coaxial cable, your field is confined between the two conductors. So, the field is actually propagating through that dielectric material between the two conductors. That dielectric material is similar to this, it is not able to respond to high frequency excitation in the order of gigahertz. Okay. So, you have that loss that comes about. Yeah, this is the question. So, so the question is, what is that we showed before? Was it electronic or molecular resonance, or this entire picture that we developed based on this electronic resonance? So, the molecular picture is essentially two atoms, right. So, you basically have one atom here, another atom here, sharing an electron, right, and this can be once again modeled as two masses attached to a spring. So, that is going to have a characteristic resonance. This graph is, I am just plotting directly from that expression for L. That's what. So, you to get that other extra this molecular resonance over here, you would have to have one more extra term, right. So I've just, in this equation, I've just had a term for the mass of an electron, but if you add one more term for the mass of the atom, right, you're tracking the displacement of the atom also. So we are putting both those pictures together here. 10 power 9 actually, sorry. Yeah, 10 power 9, yeah. No, that just comes directly from this. So you can just say even before it goes to it approaches omega naught, your response is actually scaling down by omega, right? Higher the value of omega, higher the frequency, your response is already starting to come down. Yeah, it's all coming from that expression there. Exactly. So let me give you a picture here, and then you can ask your question. So this is in frequency, right? This is actually our visible region, right? We talk about infrared, that means it's inferior to the red frequency, the lower to the red frequency. So that infrared edge is over here, and ultraviolet or superior to the violet frequency is over here. Okay. So now you can go back and see what is the dependence of the refractive index as a function of wavelength. So we remember initially when we were drawing the expression, I mean looking at the curve for refractive index, we said it's something like this. So along UV wavelengths it's actually higher, and along IR wavelengths it's lower. That just tracking this curve over here. Okay. And remember when we are talking about loss in an optical fiber as a function of wavelength, we said it's Rayleigh scattering over here at shorter wavelengths, and at longer wavelengths we said it's molecular resonance. Remember that when we were talking about optical fiber attenuation in optical fiber, we were talking about that. That resonance is over here. As you go into infrared region, you are starting to climb up this molecular resonance over here. Okay. So you can understand a lot of behavior of material by having this picture. So the term where we said we have material dispersion. Why does material dispersion happen? Because the medium responds differently for different wavelengths. That is because of the n over n versus lambda, it's not uniform. So the material dispersion can be explained with this. All the losses in the medium can be explained with this. So this is something that you should have in your mind whenever you talk about light going through a material. What is happening to that light? You have absorption or attenuation, and you have dispersion in the medium, which actually it also, the refractive index also governs the speed at which light actually propagates in that medium. All of that is coming from here. Okay. So it's not like the photons are just tunneling through this medium without interacting with that medium at all. It's more like the photon corresponds to an electromagnetic wave. That electromagnetic wave interacts with the medium, and the medium responds, and that electromagnetic wave is carried through the displacement that we are talking about here, and that is how the electromagnetic wave propagates. Huh? Y-axis is just magnitude of epsilon prime and epsilon double prime. Yes. So, we have to stay clear of that molecular resonance if you want to make sure it is actually. So, you want to be, if you are transmitting something, you want to be missing those peaks, right, where epsilon double prime is 0 is where you want to transmit information. Glass is transparent because epsilon double prime is 0 at visible wavelengths. Glass is opaque, as you go to deep UV, it is opaque when you go to infrared wavelengths. Okay. So, you can that's glass as an example, but you can take other examples also. Okay, I am really stretching my time here, so I should wrap up. Let me just finish with this note over here. So, when we talk about response of a medium, right, that response of the medium we express with as a d vector, the displacement vector, which we say is epsilon naught epsilon r multiplied by E. For an applied electric field, you get a response as d, and that response is through this epsilon r. So, this can be written as epsilon naught multiplied by 1 plus chi times E, where chi actually is called the electronic susceptibility. Okay. And this can be written as epsilon naught E, which does not have anything to do with the medium, right, and whatever response of the medium you denote by this term P, which is it's a term that we call as polarization. So, why are we calling this polarization? It denotes the polarizability of the medium. If I apply an electric field, how well does the medium align to that electric field, right, or how well does these orbitals align to that applied electric field. This final term is representing that. Okay. And and what we will see is that response can become nonlinear beyond certain values of E. So, we will come back and look at those details later. So, what you are going to be doing in this week's experiment is actually manipulating the polarization of light. I was hoping to give you some background on that before you go into that experiment. How much time do you have? Do you have any time at all? Another 10 minutes, is that okay? Yeah? Okay. P, polarization is basically a response term. The response to that. So, that is essentially epsilon naught chi times E, right, where chi corresponds to the displacement. Chi is proportional to the displacement of the electronic charge. Okay. 10 minutes is what I have. So, let me just quickly go through this. So, what you are going to be looking at is how do you manipulate light? That is what we started with, right. So, we say okay, you have a light beam coming in to this black box and your light beam is going out. Let us say the incoming light beam has got a power as a function of time like this, it is uniform power as a function of time. Can you convert it to something like this? Can you modulate this light power or light intensity or the number of photons that are going through this black box? How can you modulate that? And what we are going to see is that modulation can happen through manipulation of the polarization of light, or you can actually manipulate this by an external signal applied to this through RF waves, radio frequency waves, right. You could have radio frequency waves interacting with that light, allowing you to manipulate the property of light, or you could have acoustic waves. Imagine that by using a sound you can change the property of light. Okay. So, we are going to go into details of each one of these, but the first thing that we will talk about, and this is what you are going to be doing in your experiment, is by manipulation of polarization of light. So, very quickly, this is something I expect all of you to have come across in an electromagnetics course at some point in your life, in your student life, right. So, we say for an EM wave propagating in positive z direction, so how can you represent that? This electric field, let us say corresponding to this electromagnetic wave, can be represented in, let us say, Cartesian coordinates x, y, z and t as, if you are propagating the positive z direction, all your electric field components are in the transverse direction, transverse to that propagation direction. So, it is basically in the xy plane, right. So, you can represent this as Ax Ex plus Ay Ey, and you could have a phase difference between the x and y components. That phase difference I will represent as e power j phi. Okay. That characterizes the transverse components, and then it is going to have e power j omega t minus beta z, right. Omega t corresponds to the the time variation, and beta z corresponds to the phase accumulated during propagation. Okay. That phase is different from phi here. Phi I am talking about, if this is my x component, this is my y component, phi corresponds to any phase delay between these two components. Okay. Both these components are travelling and its accumulating phase, that is at the rate of beta z, right. But these two can actually have slightly different phase with respect to each other, which we are trying to denote by phi. Now, if phi equal to 0, then what you will find is both your Ex and Ey components are travelling together, and depending upon your relative magnitude of Ex and Ey, you would actually have an electric field that is tracing a line as it is propagating. If both of them are equal, Ex is equal to Ey, then it will actually have a 45-degree line that is tracing. So, that is what you call as linear polarization, right. So, if phi equal to 0, then you have linear polarization of light, and specifically when Ex, if Ex equal to Ey, that means that the linear polarization has a angle of 45 degrees, right. It's that is a specific condition that you are satisfying. And of course, if Ey equal to 0, then it is X polarized. If Ex equal to 0, then it is Y polarized, right. It is basically tracing a line in the Y plane as it is propagating. Okay. Now, if phi equals to plus or minus pi by 2 while Ex equal to Ey, what you will find is that your electric field vector is going to trace a path that is going to be a circle as it propagates, in the z direction, that propagates in this direction, it traces a circle. So, this you would call as circular polarization, and in circular polarization, if it is phi equal to plus pi by 2, you call it as left circular polarization, and phi equal to minus pi by 2, you call it as right circular polarization. Okay. But then otherwise, if it does not satisfy any of these, you have what is called elliptical polarization. So, the electric field vector traces an ellipse as it is propagating in this direction. Now, so those are the polarization states of light. Now, what can we do with this? Yes. Yes. Then it is basically a orientation. If Ex is predominant compared to Ey, then it is a orientation like this, right. If Ey is predominant with respect to Ex, its orientation is like this. The orientation changes, but it is always remaining linear. It always traces a line as it is propagating. Okay. Only if there is a phase change, then there will be this circular or elliptical polarization. Okay. So, the specific experiment that you are going to do is this. Suppose you have a light source, okay, and you send that light source through an element called a polarizer. Okay. The property of the polarizer is such that only that polarization component that you have aligned to that axis, it is like basically you have some molecules that are stretched in this direction. Okay. Only this polarization will go across those molecules. If you have a crossed polarization, that will be extinguished by that molecule, right. So, it is basically that is what you call as a polarizer. So, what you expect coming out of this is actually light with vertical polarization. Okay. Now, suppose you have another polarizer over here, and you have the same orientation, then what do you expect? All of that light should come straight through. So, I would draw this as a function of theta. Now, let us say that theta is 0 initially, and then I am rotating that. I am basically rotating that other polarizer. Okay. So, what do I expect to see? When theta equal to 0, then I get to see maximum light, but when theta equals to pi by 2, 90 degrees, it will extinguish that light. And then if theta goes to pi, that will go to maximum again and then extinguishing and so on. Okay. So, this is actually, this is basically the transmitted power, P transmitted. Okay. It goes like this. This is basically pi by 2 and this is pi. So, the power that is transmitted can be represented as P naught cos square of theta, right, because you basically this is equal to P naught when theta equal to 0, when theta equals to pi by 2 it goes to 0 and then with pi it once again becomes P naught, right. So, this is what we call as Mallus's law. Mallus law says that if I take a polarizer through which I am actually polarizing any light source, okay, and then so this is my polarizer, and then I use another polarizer which I will actually call as an analyzer. Okay. If I have an analyzer and I rotate that analyzer, then I would actually plot this cos square function. Okay. So, I can use this now as a variable optical attenuator. Remember in one of your experiments you use a variable optical attenuator as part of your kit. This can be a variable optical attenuator. By orienting, by changing the angle of the analyzer, orientation of the analyzer with respect to the orientation of the polarizer, you can control the amount of light that is transmitted. Okay. So, you can use this as variable optical attenuation. So, you will be given two polarizers and one light source and a detector. So, you will be actually proving Mallus's law. And then what if you introduce a component in between? How does your liquid crystal displays work? You know, you have a light source in your LCD display, you have your light source at the back end, right, and then you have a polarizer sheet. So, what comes through that is polarized light. Then it goes into each of those pixels. Each pixel has got a liquid crystal element, okay, and then you have another polarizer at a different angle. Okay. Now, without any signal applied to the liquid crystal, the orientation of the liquid crystal can be changed depending upon voltage that is applied to it. Okay. So, if without any voltage you set up the two polarizers such that it is all dark, okay, there is no light that is coming through. But then in here you put your liquid crystal and you actually change the polarization state of light that is going through, you rotate that polarization. Okay. So, let me just draw that. So, initially you have polarized light coming in, and you have a crossed analyzer. So, light that comes in here goes through here, and it cannot go through here because it is all absorbed by this material. Okay, it cannot go through here. But now I put my liquid crystal over here, right, such that I have once again polarized light, but that light polarization, so this is my polarized light after this, but after going through the polarized liquid crystal, suppose I am able to twist the polarization, rotate the polarization, so that it lines up with this analyzer over here, then I have maximum transmission. So, I can turn light on or off by changing the voltage applied to this liquid crystal. Okay. So, that is essentially what you are doing in your display or even in your projector. Certain parts it is white light, that means light is going straight through, right. Certain parts there is a particular color, red color. So, that actually goes through a red pixel which is turned on, which means that there is a voltage applied to that red pixel such that it is transmitting, and all the other colors. So, you basically have RGB pixels. Each pixel that you are defining has got RGB sub-pixels, and each of those sub-pixels has a liquid crystal element which is individually controlled by this voltage that is applied, right. So, by turning on only the red pixel, red transmission, you are going only the red color is let through, and the other blue and green are dark. They basically, there is no voltage applied to those liquid crystals. So, they are blocked. But if you want to get orange, what you do is you turn on both red and green. They mix together and they look orange over here, right. So, that is how you are generating all those colors, but essentially you are manipulating the light transmission through your liquid crystal display by manipulating the polarization of light. Okay. So, that is what you are going to actually see in the lab this week. Okay. You will. So, normally it is linearly polarized light, because the polarizers that pass this linear polarization is easy to achieve. It's actually naturally occurring. But there are some very specific applications where you need to go to circularly polarized light, and you can generate circularly polarized light from a linear polarization through a process called retardation. I think we are running out of time now, so I won't hold you guys very much, but we will talk about it in Friday's lecture.